Okay, so now that we have our data set ready and pre-processed and we have created the data generator, the next step is to define a model so that we can start training. Okay, so to start off by selecting the model, what we can do is we can go to this link. I have added this in the description below as well. So you can go through this PyTorch documentation and see what different terms mean. So for example, we have pre-trained weights. This means that the data, that the model has already been trained on a publicly available data set, for example, ImageNet, that contains a wide array of images, and they have trained the model and it has associated weights in it, and then you can use that model and refine it on your data set. Other than that, you can also use the models, but you can use it without using the pre-trained weights, which we are going to do in this experiment. We are trying to train a model from scratch to see how well it would perform on the data set that we have just pre-processed. In the next step, what we can do is we can use the pre-trained weights, and then we can use them on our training data set to see how it will work on our data. So to select the model, there is a wide array of models that is available. If I scroll down a bit, okay, so here, as you can see, there are so many classification models available with and without pre-trained weights. You can use any of these or all of these depending upon the experiments you are trying to perform. Okay, so generally if you are doing some baseline experiment, it is generally a good idea to use all these models and to do experiments on these and see what kind of results you get when you train a model from scratch on a data set. This provides you with a baseline results, and then you can use them to train more complex models, and you can go towards transformers and pre-trained weights and see what kind of things or changes you can do to the model's architecture to get better results. So just for experimental purposes, for this project, I have taken the DenseNet model. Here, as you can see. Okay, so in the first two lines of code, what we are basically doing is we are just checking if our device is using CUDA or not. This is generally useful when you are using this on the system. Here I already have these two GPUs and I intend to use them. I'll show you the lines of code that I use to make sure that I make use of both these GPUs that are available. Okay, so in these lines of codes, as you can see, I've used the DenseNet model and I have set the pre-trained weights to false. This means that it is not going to use the pre-trained weights that it has been trained on. So by pre-training, what I mean is that the DenseNet model has been trained on a very large data set, which is this ImageNet data set. It contains around this number of images, which are quite so many images. And then if I show you the kind of images that they have used, as you can see, they have these fields, cars, animals and everything, but we are using a medical imaging based data set, right? And I want to see how the model would perform when it doesn't have any sort of pre-learning or transfer learning on it. So for that purpose, I set pre-trained to false. You can set it to true as well, but you might have to make some changes in the code to make sure that you can use this pre-trained weight. We will experiment this in another video to see how our data would work using the pre-trained weights. Okay, so here I have just used this model. I've taken it from the internet directly. There is no rocket science in it. You can simply just copy and paste it over here, and as you can see, we have 4 classes that we want to predict, so that is why it is set to 4 over here. Okay, so the next thing is that we are using our model on GPU, which is why we have moved the model to the device, either it is GPU or CPU. I'll show you the lines of code that we use to make sure that we are parallelly utilizing these 2 GPUs as well. Okay, so this function is basically for visualizing the number of parameters that we have, the amount of trainable parameters, non-trainable parameters, the model size that we have. All these statistics become very useful when you are doing research on a certain data set. What you can do is you can simply log all these details on a table on either Notion or an Excel sheet, so that you can refer back to it when you want to understand what kind of results you had and what was the size of the model and how well it performed. If you have a model size that was much less and it performed really well. So for example, there is MobileNet, there is VGG16, which are I think less in size compared to the DenseNet model and the transformers. So you can see if the model size is less and the model is performing well, you can use that model based on the results that you have stored in the sheet. Okay, so to make use of the parallel GPU, I have these 3 lines of codes. When I run these, basically my code will now leverage these 2 GPUs parallelly and will put load on them parallelly so that I can have better execution of the code and faster processing. Next, I'm calling this get model summary function to get the summary of the model. As you can see, the total amount of parameters I have is this, and then this I am training the model from scratch. I'm not doing any pre-training, which means that all these parameters will be trained. There is a zero number of non-trainable parameters because I'm using the model from scratch, and the size of the model is 26.54 MB. We have defined our model. The next step is to have a comprehensive sort of a code snippet that contains code for both evaluating the model and training the model. First, we'll train the model and then definitely we'll evaluate it. So for that, I have different hyperparameters. The first one is the learning rate, which is set to 0.001, but I didn't want it to be a fixed learning rate. I want to make sure that it is adaptive so that I can get the best of the results from the model and the training that I'm doing. So for that, I have used an adaptive learning rate scheduler, which is here, which looks something like this, and then the optimizer that I've used is Adam optimizer. And another thing that I've used to make sure that the model doesn't overfit is the weight decay regularization technique. This technique allows to make sure that the model doesn't overfit. Next thing is this patience. This patience is basically the number of epochs that I want to train my model until I know that it is providing the same results. So for example, what early stopping does is it makes sure that the model doesn't overfit. How it does this is that when a model is training for a certain amount of, for example, 50 epochs, it would train for 10 epochs and see if the model's performance is not improving. So for example, for 10 consecutive epochs, if the model's validation loss is not decreasing or the validation accuracy is not increasing, it remains the same, or it is decreasing than the highest one that we have achieved, then it would stop training. So for example, if we have 60% validation accuracy and it is not improving for the 10 epochs, 10 consecutive epochs, it would stop training. This would allow us to firstly save memory and save our resources, and another thing that it allows us to achieve is that it reduces the model's risk to overfit. So that, which is why I've set this patience to 10. Another patience is also set over here, which is 3, which is for the adaptive learning rate scheduler. This means that for 3 consecutive epochs, the learning rate would remain the same, and if the performance is not changing, it would change the learning rate adaptively to make sure that the model trains effectively. Okay, so these are all the hyperparameters that we have. We have set the batch size to 32, and we have all these things over here. The next thing is to have an early stopping class. This is basically doing the same thing that I explained earlier. It would go around for a consecutive amount of epochs, and if it doesn't see any improvement in the performance of the model, it would stop training, or it would trigger early stopping. Next thing I have also defined is to save the best model weights. What it would do is it would allow me to use these weights in the future to make prediction on test data sets that I might have. I can simply download the model's weight. It would be basically stored over here. If I click on this small arrow button, okay, let me just quit it, and then if I hit on the arrow button, I can see that there is this output folder, and in this directory the model that I want to save will be stored. So for example, if I click over here, this is the model that I was training earlier on, which is why it is saved over here. The same thing would happen with the DenseNet model. The DenseNet model weight would be stored over here, and we can use them later on. We can download them from over here and use them later on our test data set. Next is this train and evaluate function. This train and evaluate function contains all the things that we have defined, and it would train the model. One thing that I also want to mention is this DQDM. What it does is it shows us with the progress bar so that we know how much training has been done for each epoch. It becomes really daunting to me when I can't see the progress. I like to see how much progress has been done, how much batches has the a model gone through, so that I can have an idea of the time that each epoch would take. Okay, so after defining this entire function, the next function that we have is to make evaluation on the test data set. For that, we can print our classification report. We can also see the sensitivity for each class to see how well the model is performing for each class. We can see the accuracy of the model, the prediction, the F1 score. These are all the things that we can use, all the measures that we can use to measure the performance of the deep learning model that we are using. I have added all this in one code snippet so that we can later use these on our test data set and see how it works. This last function is also really interesting. It allows us to see the predictions that the model has made on the test images themselves, and also shows us with the confidence that the machine learning model has on that prediction. So for example, if the model is predicting if that image is ischemia, it would have around 80% or 90% of confidence, which would allows us to understand how much confident the model is in making that prediction. So after adding all these things over here, we can simply run this, and then we can start training. This model would train for 50 epochs or up until early stop is triggered. Okay, so I'm going to click on OK. First, let me close this, and if I click like this, okay. So now the training has started, and if I show you over here, you can see that both my GPUs are working parallelly because I use the parallel working settings in the above code snippet where we define the model. So now, as we can see, our model is working parallelly. Now we'll wait until the model completes its training, and then next we can see how we can basically evaluate the model. Another thing that I'd like to mention is that if you are sure about the lines of code that you have already mentioned, you can simply run them like this. Now they will run after the 50 epochs have been trained, right? But in Kaggle, it provides you with another very interesting feature in which you can click on the save version button, and you can name your version anything, or you can also keep it version 1 if you like, and then you can simply click on the save button. What it would do is it would add this over here, and now you can simply open the logs in viewer. And here you can see everything, how the code is running, how much time it has taken to run, and then finally the output that it would provide will be stored over here. You can simply go ahead and download the model weights from over here or over here as well. So what happens in my experience is that when we are training the model enough, I leave the system over here and I come after a while, the training would stop and the accelerator and everything will be gone, meaning that the session would stop, right? If the session stops, the output that we have over here can also get lost. If we have clicked the save version button and we have saved the version of it, we can definitely go ahead in the future and access the output files from over here. Kaggle makes it very easy for us to access things this way. So this is how the training is going on. Okay, the training is fairly quite fast. If I see, it is taking around 2 minutes to complete one epoch, I believe. Okay, so now we wait until it completes its execution and we can move forward with this evaluation of the model and everything. So now the training is complete. Let's see how many epochs we had until the early stop was triggered. So if I go down, I see that the best model weights were saved when the validation loss was 0.5441. Okay, so if we move down for the next 10 epochs, I think there was no improvement in the validation loss, because of which the training has stopped. Okay, so if we look at the train and validation curves, loss and accuracy curves, we can see that the validation accuracy is fluctuating. Okay, and the training accuracy up until the 25th epoch onwards, it was quite consistent compared to the validation accuracy which was fluctuating. Okay, And as you can see with the loss as well, the loss for the validation dataset has been fluctuating, and for training it has been smooth compared to the validation loss. Okay, so if we move down a bit and look at the classification report that we printed, so as you can see, the accuracy of this model is 0.75, which is 75%, and the precision for each category is 76%, 78%, and the sensitivity F1 score and support is also provided. Okay, if we look at the sensitivity for each class separately, we can see this is the sensitivity or recall. For each class, we get something like this. As you can see, the sensitivity for infection is the highest compared to the other categories, and the second is the both category, then comes the ischemia, and finally none. Okay, so to get a better idea of how many images were correctly classified based on the ground truth that we provided, so we look at the confusion metrics, and as you can see, most of the both images have been classified correctly. However, there are a few images which true label is on the y-axis and predicted label is on the x-axis. Okay, so as you can see, for both we have 97 cases which have been misclassified as none. Even though they had both ischemia and infection, they were classified as none. Other than that, 5 cases were both, but they were classified as ischemia. But most of the cases, which were around 400, were actually both, and they were also predicted as both. So this is how we look at the confusion metrics. We see what the true label is. So for example, in this case, the true label is none. So we can see that around 135 cases have been misclassified as both, and 97 of the both cases have been misclassified as none. So I found so I find these two classes to have the most issues when it comes to the predictions. I think the machine learning model is confused between the none category and both category, because the maximum amount of images that are misclassified belong to either the none category or both. Okay, another thing that we discussed earlier before we started training the model was that we have a function over here that allows us to visualize the predictions, and we can also see the confidence score of those images. So this is the final output. So GT is the ground truth, prediction is the prediction made by our model, and the confidence is how much confidence the machine learning model has in making that decision. So for example, if we look at this image, it has been misclassified by the model as both, and it has a confidence of 53% that this image is indeed both. If we look at a case that was none and also predicted as none, so for example, in this case, the ground truth was none and it was also predicted as none, and it has a confidence score which is quite good, which is of 0.81, which means that the model is quite confident that this image is actually none, which is a good thing for us. Same goes for infection class. It has a confidence of 94%. This has a confidence of 99%, which is actually very good. So most of the images have been correctly classified. There are a few, I think, that belong to the none and both categories that has some issues in them. One more thing I'd like to mention is that once you are done training the model, you can go over here, click on this arrow, and here you have the output, right? If we click on this drop down over here, we can see that the model that we have just trained is present over here. It has the weights of it. We can simply click on these 3 dots and download the model if we want to keep it for our own use. Other than that, if we just want to see if it is stored in our Kaggle, we can click here on these 3 images, and then we can click on these 3 dots and open in viewer. Once we do this, we will now be able to see the output over here as well. So this shows us the notebook that we have been working on so far. This is the input that we have provided, which is the data set that we have just used. This will provide us with the output that we have, which is this one, which is our model that we have just trained. And this provides us with a time that it took to successfully run this notebook, which is around these seconds. You can convert them into minutes or hours to see how much time it took for you to train the model. In the next video, we will be working on some other projects like breast cancer detection or brain tumor segmentation based projects, and we'll see how we can leverage this platform, the GPU that it provides and everything, and how we can do different experiments and understand different concepts. So I hope you found this video useful, and if you did, please like the video and also comment if you have any suggestions. I will see you guys in the next one. Thank you so much.